HDMI connection now instead of regular projector cable connection. The only problem is I think I need to do something with the sound because I'm noticing, anyways, I'll have to figure this out. Things to figure out later. What we're going to ask ourselves today, Curtis, is, hey, what if you have more than one battery? Okay. What if you have more than one chairlift, in my analogy? What if you have more than one voltage source? So this lesson I called Voltage Difference. We're going to finish up, actually, at the end of this lesson, analyzing a circuit that's well beyond Physics 12, but I'm going to let you know we can still handle it just fine, it turns out. And if I've done my job right, most of this lesson should be intuitive, I hope. So, here's the first question. Suppose you were to connect two 1.5 volt cells in series, like in that picture. What do you think the net voltage measured by the voltmeter would be? If you have a 1.5 volt battery followed by another 1.5 volt battery, what do you think that's the same as? Alex, 3 volts. 3 volts. It says, explain your answer using principles of physics. I'm not going to bother. You know what? In my chairlift analogy, here's what it means. You went up a 1.5 volt high chairlift, and then you got another 1.5 volt high chairlift and went up that. Oh, how high have you gone? What's the voltage? 3 volts. We will put batteries in series in certain small devices. So I wrote down here, in many portable appliances, CD players, flashlights. Several years ago, when you were young children, or perhaps before you were born, we used to actually carry music around on physical devices. They were called tapes, and then those eventually became CDs. And a CD player was a device that you carried around, and it played music for you. However, it physically caused a CD to rotate very, 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 very fast. Because the CD was rotating, it had kinetic energy. Where did that kinetic energy come from? Batteries. Problem is, you usually needed more than just 1.5 volts. Most batteries, by the fact, all the standard batteries are 1.5 volts. So this is 1.5 volt, a little AA is 1.5 volts, a little AAA is 1.5 volts. The difference is this can supply charge for a lot longer. This has way more electrons to give up. A smaller battery isn't going to last as long. Okay, so anyways, CD players. I wrote here, in many portable appliances, CD players, flashlights, 2 or even 4 or more batteries are connected in series, as in the diagram above. In series, the effect is to increase the total voltage applied to the device. It is a way, Callum, for me to get 3 volts without having a 3 volt battery. The only problem is this. Total voltage equals total current times total resistance, yes? Get the I by itself. If the resistance doesn't change, so for example, in a flashlight, it's the resistance of the bulb. In a CD player, it's the resistance of the motor. If that doesn't change and your voltage gets bigger, what happens to the total current? And when we're talking about a battery, Alex, total current is the electrons coming out of the battery. You know what? That stack that you see, it would drain those batteries twice as fast. You'd get way more voltage. It's not going to last as long. It's a trade-off. Sorry. Okay? So I wrote here, you now have twice or 4 times as much current flowing through it as it would otherwise. The batteries won't last as long in series, but they'll power a bigger device. I guess that kind of makes sense. If you are powering a bigger device, you're using energy up faster, the batteries shouldn't last as long. What if we connected them in parallel? Well, what we're saying is the current, here's total current, but then it splits up. Some go through the first battery, the first chairlift. Some go through the second battery, the second chairlift. And then they meet up here. What's the total voltage? What's the total height of this mountain, of this circuit? 1.5 volts. In fact, if you wanted to measure the voltage, I wrote here, what meter would we use to measure this effect? We could put a voltmeter actually across the only resistor, because no matter what, we have to lose that voltage. This would be that doesn't increase your voltage, but this has an advantage in that each battery is only supplying half as much current. And if each battery is only supplying half as much current, how long will each battery last? Twice as long. In your fancy schmancy graphing calculators, I know a few of you have them, for example, I noticed that this is 4 batteries in parallel. This lasts quite a while. In fact, right now I think I'm on to 2 years with this batch. Okay? This only needs about 1.5 volts, but I can share the load and I can get the batteries to last longer. You also will see sometimes in some remote controls a combination. You'll see 2 batteries in series, 2 more batteries in series, so that system needs 3 volts, but if we just did it that way, it would run dry so fast, we put a second set in there so that your batteries last a bit longer. Your remote controls, almost all of them could run off of just one of these, but they would only run for about a week or so. Engineers, designers, they know you don't want to replace your battery every week. You consider that a piece of garbage, so they find ways around it. Is that okay? So we have series, we have parallel, and hopefully it kind of makes sense with our ski hill analogy. Parallel, you're not gaining extra height, but you're splitting up the current. The batteries will last twice as long. In series, you're gaining extra height, but you're going to be using more current. I guess you could say, oh, it's a higher mountain, it's more popular, more skiers want to go there, I guess. You can do one more setup, Sammy. You can have the batteries facing each other, like example 3. So I wrote here, rechargeable batteries, they are recharged by connecting them to a cell that forces current back through the original cell. You connect a small rechargeable battery to a bigger voltage in the opposite direction, like this picture here. If I connect a 1.5 volt battery to a 6 volt charger, then first of all, what would be the direction of the current right here, towards the left or towards the right? How high? 1.5 volts. How high? Which way is downhill overall? Yeah. The current is going to go this way. We're going to force it backwards through the battery. The current is going to go that way. What do you think the net voltage would be? Now, our ski hill analogy, Callum, still sort of works. You go up this chairlift right here. How high are you? 6 volts. Then you're going down this chairlift because you're going against the direction. You're going from positive to negative instead of the other way around. This is like riding a chairlift partway back down a hill. What do you think the net voltage here is? What would make sense? 4.5 volts. Oh, and then you'll notice if I still have 4.5 volts right here, we had to add a protective resistor right here. If we didn't have that, that extra voltage would go into heating up the wires, and that would be bad. This is why in almost every little rechargeable system, as soon as you plug it in or hook it up, there's a little green or red light that goes on showing you that it's recharging. Actually, that red light is the protective resistor that's bleeding off the excess voltage that you don't want to go into heating up the batteries. They do make chargers now that don't have that light, but that was always the simplest one. That little light was doing its job. It was saying whatever extra voltage, I'll use up. Kind of clever. Oh, and it also gave you the reassuring, oh, we're recharging with a light. Let me pause for a second. Okay. So in terms of and again, explain your answer using principles. I think we have. I'm not going to get into a big, long, I could do a Kirchhoff's law, Ohm's law thing, whatever. So in terms of our ski hill analogy, cells in series, like example 1, are like a 2 chairlift ride to the top of the mountain. Cells in parallel, like this picture here, are like, you know what, you can take that chairlift, you can take that chairlift, but they both lead to the top of the mountain. So nobody gains extra height. Cells facing each other, you know what, that's like 1 up chairlift and 1 down chairlift. Yeah, turn the page. So if they give me multiple batteries, the key that I try and do is I always like to find out which way is overall downhill, Oh, and hopefully you're starting to clue in why, even though technically in all of these circuits, Hakeem, the electrons go this way. Hopefully you're seeing why it's so much nicer to have current move from positive to negative. It certainly makes more sense mathematically for us to wrap our brain around, right? Anyways, what we want to do is identify where our highest positive means higher, negative means lower. Find your highest positive. That's downhill from there. Current flows downhill from positive to negative. But if you go through a battery from positive to negative, that's downhill. You've lost voltage. I was going to do example 4. I'm going to say, meh. And instead, we're going to jump to example 6. Example 6. Example 6 says, find the voltage difference between points X and Y, and then find the unknown currents and voltages using Kirchhoff's laws. Note, this is well beyond Physics 12 technically, but I want to show you that we can handle it. In fact, I think I stole this from an old physics college textbook. I'm going to zoom in. How am I going to handle this? Where's the biggest hill, the biggest voltage source? You know what? That's downhill. That's the top of the mountain. Which answers at least part of my question as I go skiing. No, yes, right? And we're going to the right here. Now it looks like they've told me we have some skiers coming in this way. We have skiers coming to the right this way. When they meet, what direction must they now go? You know what? They must go that way. That's downhill, that's downhill. That's downhill. Okay. Did they tell me total current anywhere? Nope. Did they tell me any current anywhere? Yep. Which one, Michael? Okay, so what's the current right here? What's the current right here? Gotta be 0.5 amps because there's no junctions between here and here. So I've got 0.5 amps coming out, 0.5 amps must be going through, right? So let's add that. I'm going to go 0.5 amps. Hey, I know 2 things on that resistor. I know 3 things. What's the voltage drop in that resistor? In your head, what's 3 times a half times 0.5? What's half of 3, Michael, reaching for a calculator? Oh, sure you were. I believe you. Anything you say. Curtis, what'd you say? Okay, I lose 1.5 volts. Let's go skiing. Let's see here. This looks like a nice ski run. That's going downhill the whole way, yes? Okay. How high? 4 volts. How high? Don't know. What do I lose here? What must I lose here then? Hakeem, gotta be. I still don't know 2 things over there, but okay, that's a start. Let's go skiing some more. Now, the one I'm going to try and avoid, don't write this down, is this one. I don't want to go uphill through the chairlift because that's confusing. So there is another nice all downhill run. I can go like that. I think that's all downhill all the way, is it not? And that's what I'm best at. So let's ski that run. Cliff, how high? Don't know. Was I able to get to the bottom? What must I lose here? I know 2 things. I can also now tell you the current there. Current is voltage divided by the resistance. Cliff, no. Michael, in your head, what's 3.5 divided by 3.5? Wow, look at that. And I can answer up here where it says I equals, that's got to be 1 amp right there. Yes? Which way is that 1 amp flowing? To the left or to the right? To the right, to the right, to the right, to the right. Now right here, what's coming up from the bottom? How many amps must be sitting right there? How many amps are coming to the right? How many amps are coming to the right? 1. How many amps are coming up? 0.5. What's the current sitting right there? Got to be 1.5 amps. How's that help? What's the current in the mystery resistor, R? 1.5 amps. Do I know 2 things? Well, then I know 3 things. In fact, technically I know 4. I haven't been asking you to find power. I did it the first lesson. I flogged it to death, but I'm assuming you can all go power equals VI or I squared R or whatever you need to, right? Hey, what's the resistor of that resistance? R is going to be V over I, yes? R is going to be, what was V? 2.5 over 1.5. You get 1.67 ohms? Yeah. R equals 1.67 ohms. Is there any other blanks I was supposed to fill in? Oh, they also said find the voltage drop between location X and location Y. Now I can tell you, because now I think I can ski this yucky run. I saved it for last. How high? 6. What do I lose? Going through here, can I get to the bottom? What must this net voltage be? A drop of what? Come on. The voltage between X and Y is 2.5 volts. It could be, call it positive, could call it negative. It depends which way you decided to go through it. I think, Kelly, going this way, I lose 1.5, gain 4. That would be a positive increase. Going in the way of the overall main current, I lose 2.5 going down that way. But the change in voltage is definitely 2.5 volts. Hard, we were able to handle that, actually. And I'm not going to give you one anywhere near this tough on your test. Okay? What's your homework? Number 1. Number 2. 3 is good. 4 is good. Again, going to give you lots of practice. 5 is good. 6 is good. Take a look at 5 and 6. I'm going to argue those are the same question. Look at the circuit. Except in number 6, I didn't give you the resistance numbers. I just told you they were identical light bulbs. If they're identical, what can you tell me about all of their resistors in question 6? They are? So if you don't like, you can try doing it algebraically, but if you don't like doing it algebraically, just let A, B, and C all be 2 ohms or 5 ohms or some. Pick a nice number. Don't let them be 19 ohms, because when you do the 1 over reciprocal, you're going to get yucky stuff, okay? But you should be able to have an idea of what happens by your answer from number 5. You should have a good idea what's going to happen with number 6, because it's the same circuit, essentially. It's just in number 5, the resistors are differences, and they're different, and there's numbers. 7. Skip 8. 9. 10. 11 falls apart, I think. I see 2 resistors with 2 things. 11.